For anyone following the AI space, it's pretty clear how rapidly artificial intelligence is becoming part of our lives, right?
Absolutely. It's everywhere.
From the smart assistant helping you organize your day to those, personalized recommendations that somehow seem to know exactly what you want, maybe even before you do. AI is truly pervasive.
Mm.
But underneath all the headlines, the real engine driving a lot of this often comes down to something called machine learning. So what is machine learning fundamentally, and how does it actually learn to do all these incredible things?
That's a really great question. And it's fascinating because machine learning isn't just one single thing. It's a core, a really dynamic branch of artificial intelligence, but it's broadly categorized into three main types.
Three types. Okay.
Yeah, exactly. And each type has its own unique way of learning, relies on different kinds of data, and it's designed to achieve very specific goals. It's less a single entity and more like a diverse toolkit, of powerful approaches.
And that sounds like our mission for today then. We're taking a deep dive into these three foundational pillars: supervised, unsupervised, and reinforcement learning.
That's right.
Our goal is really to break down what makes each one tick, understand their distinct mechanisms, and maybe clarify why knowing these differences actually matters to you, the listener.
Hmm.
The sources we've looked at offer a really detailed picture of each, from the basic principles to their sometimes surprising everyday impact. So let's jump right in with what's arguably the most common one.
Sounds good.
When we talk about machines learning, I think the first thing many people probably picture is supervised learning. It feels like learning with a very specific instruction manual, maybe, where there's a teacher constantly giving you the right answers. It feels kind of natural.
It really is, and that's a perfect way to put it.
Yeah.
Supervised learning is basically all about training models using what we call labeled data.
Labeled data,
Oh,
right?
yeah. This means that for every piece of input data you feed the model, you already know the correct output. Think of it like giving a student a quiz, but you've also given them the answer key right alongside it.
Ah, okay. Makes sense.
The model gets presented with the input features, which are, all the relevant details, like maybe the number of bedrooms, square footage, location, if you're trying to predict house prices.
Right.
And alongside that, the target label, which is the known correct output, like the actual sale price of that specific house in your data set.
Okay.
So the model's entire job during this training phase is to figure out the patterns, the relationships between those input features and the target labels, so it can then accurately predict the output for totally new data it hasn't seen before.
So it's essentially building this kind of complex rulebook from all those labeled examples it's seen. And I'm guessing this foundational approach, it isn't just one single thing either, right? It probably branches out.
Precisely. Yeah, supervised learning primarily tackles two main kinds of tasks that, honestly, you probably interact with constantly, maybe without even realizing it.
Okay.
The first one is regression. Now, this is used when the output you're trying to predict is a continuous value.
Continuous, like a number that can be anything.
Exactly. A classic example is weather prediction.
Yeah.
You're forecasting a temperature, maybe 25.3 degrees Celsius, or predicting rainfall in inches. These are numerical values that can fall anywhere within a certain range.
Got it. Okay, so that's regression. What's the second type?
The second main type is classification. And this comes into play when the output belongs to a specific, discrete category.
Discrete category, meaning?
The outcome isn't a continuous number, but rather a choice from a predefined set. It could be as simple as just two possible outcomes, like yes or no, true or false. A perfect example is spam filtering.
Oh, yeah.
An email is classified into one specific category. It's either spam or it's not spam. There's no in-between value.
Okay, that distinction is clear. Regression for numbers on a scale, classification for distinct buckets or labels. So what kind of algorithms are doing all this heavy lifting in the background? Is it super complex math?
Well, it can be, but it's a mix. Some of the really common algorithms you'll run into in supervised learning include things like linear regression, which is pretty foundational for understanding those straight-line relationships.
Yeah.
Then you have decision trees, which make predictions by following a sort of series of choices, almost like a flowchart.
Oh.
And of course, the really powerful artificial neural networks, these are inspired by the human brain, and they can learn incredibly complex, nonlinear patterns, especially in huge data sets.
Neural networks, always hear about those. So bringing it back to us, the everyday users, where are we seeing supervised learning in action? Maybe places we don't even notice.
Oh, it truly is everywhere. It's powering so much of our digital world. You'll find it actively working in, say, fraud detection. Systems learn to flag suspicious transactions based on tons of historical examples of what was fraud versus what was legitimate.
Makes sense.
Image classification is massive. Think about how your phone recognizes faces in photos, or how it tags objects,
Yeah,
or how self-driving cars need to identify traffic signs. It's working behind the scenes in your email spam filter, making that call on what reaches your inbox.
definitely use that one.
In medicine, it's assisting in medical diagnosis, helping predict the likelihood of a disease based on patient data. It's also used in price prediction, like forecasting stock prices or real estate values, and it's widely used in natural language processing for tasks like figuring out the sentiment of a review or even predicting the next word you're about to type. The crucial thing to remember here, though, the bottleneck often, is the need for really good, extensive historical labeled data. It struggles sometimes to detect completely new types of fraud, for example, or classify novel images until it gets enough labeled examples of them.
That's a really powerful point about relying on that labeled data because, let's face it, getting perfectly labeled data for every single problem must be a huge, often expensive challenge.
It really can be.
So, if supervised learning needs this direct teaching, these labels, how do machines tackle problems where the answers aren't given upfront? What happens when you're kind of exploring the unknown?
Right, and that's exactly where we pivot to the second pillar, unsupervised learning. And it's a completely different approach, a different philosophy almost.
Okay.
Imagine, like you said, throwing a machine into the deep end. You give it this massive pile of unorganized information, unlabeled data, and essentially tell it, okay, figure it out yourself.
No instructions, no answers.
Nope. Unsupervised learning algorithms are designed specifically to analyze and group these unlabeled data sets. The model has to find the hidden patterns, the structures, the relationships within the data all on its own. There's no human guidance, no reference points, no pre-existing labels telling it what's what, no supervisor, no answer key, just the raw data itself.
Okay, so it's left completely to its own devices. How does it even start to make sense of things without that teacher? What's the core mechanism there?
It's fascinating. In this type of learning, the machine takes that raw, sort of random-looking data and essentially starts grouping it. It does this based purely on similarities, patterns, and differences it discovers within the data. It's looking for inherent structure.
Okay.
So the main goals are really threefold. First, analyze the internal structure of a data set. Second, group data points based on those similarities, maybe creating clusters of things you never even knew were related.
Interesting.
And third, often, to represent that data in a more compressed format. It extracts the most useful information or features, which makes the data easier to process, easier to visualize later on.
That sounds incredibly powerful, especially for uncovering things we might not even know to look for. So, what are the main jobs, you could say, that unsupervised learning excels at? What specific tasks does it do?
Yeah, there are three primary tasks it's really good at. First is clustering. This is all about grouping similar data points together into sort of natural clusters. Think about segmenting customers into different behavior groups based only on their purchasing habits without anyone telling the algorithm beforehand what those groups should be.
Right, discovering the groups organically.
Exactly. Second is association. This is where the system finds interesting rules or connections between different data points. The classic example is the market basket analysis, discovering that customers who buy, say, diapers also tend to buy baby wipes, finding those links.
Ah, the people who bought this also bought.
Yeah.
Recommendation.
Precisely. That often comes from association rules. And third is dimensionality reduction. This is about compressing really large, complex data sets, think data, with hundreds or thousands of features, while still keeping all the important underlying information. It makes the data much easier to manage, analyze, and understand.
The idea of discovering new, previously unknown patterns that really feels like a potential aha moment generator, like finding hidden treasure in your data.
It absolutely can be.
What are the big advantages here compared to the supervised methods we talked about?
Well, you've hit on the main one, that ability to discover completely new, previously unknown patterns in data that a human might just never have spotted is a huge advantage. It can reveal hidden structures, novel connections. It can fundamentally change how we understand complex systems.
Wow.
And practically speaking, because it doesn't need that often time-consuming and expensive process of human data labeling.
Right.
On there. Unsupervised learning is generally easier, faster, and frankly more cost-effective to get started with. Some common algorithms you hear about in this space are the a priori algorithm for finding those association rules, Gaussian Mister models, GMMs for more sophisticated clustering, and principal component analysis, or PCA, which is fantastic for simplifying complex, high-dimensional data.
Okay, so we've gone from the teacher-guided learner in supervised to the self-sufficient explorer in unsupervised. Now, what about the third type, reinforcement learning? You mentioned it earlier. This one feels different again, almost like teaching a child to ride a bike. Lots of trial and error, learning from falling down and getting back up again. It sounds very dynamic, very interactive.
That's a perfect analogy, honestly. It captures the essence really well. Reinforcement learning, or RL, is a unique branch. Its focus is on how an agent, that's basically the machine or system being trained.
The learn.
Exactly. The learner. How that agent should make decisions within a specific environment to achieve the highest possible cumulative reward over time. Now, unlike supervised learning, it doesn't rely on pre-existing labeled data. And unlike unsupervised, it's not just about finding patterns passively. It's all about direct experience and active interaction with its environment.
So if there's no pre-labeled data and it's not just looking for patterns, how does this agent actually learn? What's the mechanism in this trial and error world?
Well, the agent learns by doing. It performs a series of actions within what's often a complex, maybe even unclear environment. After each action it takes, it gets immediate feedback. This feedback comes in the form of rewards for actions that are good or beneficial towards its goal, or penalties for actions that are incorrect or detrimental.
Rewards and penalties, like points in a game.
Sort of, yeah. This whole process closely simulates the trial and error method that humans, and animals too, use to learn new skills. Think about it. A robot trying to learn to walk. It might get a positive reward for moving forward without falling, and a negative reward, a penalty, for falling over.
Okay.
It continuously adjusts its strategy, its policy, trying to maximize those positive rewards over the long run. Eventually, it learns the optimal sequence of actions to achieve a specific goal, like walking efficiently.
To really get our heads around this, we probably need to understand the moving parts. What are the key components, the essential pieces that make reinforcement learning actually work?
Good question. There are typically 5 essential components that define the RL framework.
Yeah.
First, you have the agent itself. That's the learner, the machine being trained.
Got it.
Second, the environment. That's the setting, the world, the simulation where the agent operates and interacts.
Where the learning happens.
Exactly. Third, the state. This refers to the current situation or configuration of the agent and its environment at any given moment. What does the world look like right now? Yeah.
Fourth, the reward. These are the predefined rules or signals, that feedback mechanism that tells the agent if its last action was good or bad, guiding its learning. The positive or negative points.
Precisely. And finally, fifth, the action. This is the specific movement, the decision, or the activity performed by the agent within that environment.
Agent, environment, state, reward, action.
Okay, and what's really, really crucial to understand about reinforcement learning, setting it apart, is that the correct answers, the optimal actions, they aren't given beforehand. The agent absolutely must learn them through continuous experimentation, through that trial and error.
Right.
This leads to a very unique challenge or characteristic, the need to balance exploration versus exploitation.
Exploration versus exploitation, what does that mean?
Well, the agent needs to explore. It needs to try out new actions, maybe actions it hasn't taken before, to see what happens, to discover potentially better sources of reward. That's exploration.
Trying new things.
But it also needs to exploit. It needs to leverage the knowledge it already has, sticking with actions that have proven successful and yielded rewards in the past. That's exploitation.
Sticking with what works.
Exactly. Finding the right balance between trying new things and sticking with known good strategies is often the biggest challenge in RL, and it's key to achieving really strong performance. Too much exploration, and you never benefit from what you've learned. Too much exploitation, and you might get stuck in a suboptimal routine, never finding a better way.
That balance sounds tricky. This whole approach feels incredibly sophisticated, maybe the closest to how we as living beings actually learn from interacting with the world. So where are we seeing reinforcement learning making a real impact today?
It's making huge strides, especially in cutting-edge fields. It's absolutely fundamental to modern robotics, teaching robots how to navigate complex, unpredictable spaces, how to grasp objects they've never seen before, how to perform intricate assembly tasks. It's completely transformed electronic games. You hear about AI learning to play and master incredibly complex games like chess, Go, even complex video games, often reaching superhuman levels.
Yeah, beating the world champions.
Precisely, and often just by playing against itself millions and millions of times, learning through pure RL. You also find it in industrial process control, optimizing complex manufacturing lines for better efficiency, less waste. And critically, it's playing a huge role in developing the advanced control systems for autonomous vehicles.
Self-driving cars.
Yes, helping cars learn to navigate dynamic traffic conditions, make safe split-second decisions, even learn complex maneuvers like parking in tight spots, all through simulated and real-world trial and error.
Okay, incredible stuff. So we've unpacked each of these learning paradigms now. We've seen supervised learning with its helpful teacher and labeled data. We've seen unsupervised learning as the sort of intrepid explorer finding patterns on its own. And now reinforcement learning as this persistent trial and error master learning through interaction and feedback. It's been quite a journey through these pillars.
It really covers the main approaches.
But now, maybe for the real aha moment, how do they truly stack up against each other? Understanding their core differences feels like the key to knowing why you'd pick one over another for a specific problem.
Absolutely.
Yeah.
And if we connect this back to the bigger picture, the distinctions become pretty clear across several key areas. Let's start with the most fundamental, the type of data they need.
Okay.
Supervised learning, remember, explicitly requires labeled data. Inputs paired with known correct outputs. You absolutely need that answer key.
Right. The teacher needs the answers.
Exactly. Now, in stark contrast, unsupervised learning works with unlabeled data. No known outputs provided. The model has to discover patterns entirely on its own.
The explorer has no map.
Perfect analogy. And then reinforcement learning is unique again. It doesn't really require a pre-existing data set in the same way. It generates its own data through interaction, learning through trial and error within its environment to achieve specific goals.
Okay. Data requirements. Labeled, unlabeled, or non-interactive. What about their fundamental learning methods? How do they actually acquire knowledge?
Their methods are quite distinct too. Supervised learning learns from specific examples provided. It's like a student given practice problems and their solutions, learning directly from those correct answers.
Learning from the answers.
Unsupervised learning, on the other hand, discovers patterns independently. No guidance, no answers. Think of a student trying to understand a complex subject just by reading through lots of material and connecting the dots themselves, finding the structure in the information chaos.
Finding the patterns alone.
And finally, reinforcement learning learns through that constant interaction loop with an environment, getting rewards and penalties for its actions. It's very much like learning to ride that bike or drive a car. You learn by doing, by practicing, and getting immediate feedback, good or bad.
Learning by doing and feedback. Got it. So these different methods and data needs must mean they have quite different goals too, right? What are they ultimately trying to achieve?
Absolutely. The primary goal of supervised learning is usually prediction and classification, making accurate forecasts or assigning correct categories based on that historical, labeled data it learned from.
Predict or classify.
For unsupervised learning, the main aim is to discover those hidden patterns, to group data based on inherent similarities, and maybe to simplify complex data sets by finding their underlying structure or dimensions.
Discover structure.
And for reinforcement learning, the core objective is to improve performance over time, to learn a strategy or policy that maximizes those cumulative rewards within its interactive environment. It's about making optimal sequences of decisions.
Maximize rewards through decisions. And these different goals naturally lead them to shine in completely different applications. Can you give us a quick recap of where each type is typically the best fit?
Of course. So supervised learning is really your go-to for problems like weather prediction, medical diagnosis based on patient history, image recognition where you have labeled examples, or spam filtering, anywhere you have plenty of past examples with clear answers to learn from.
Problems with known answers in the past.
Exactly. Unsupervised learning is perfect for things like exploratory data analysis, when you're not sure what you'll find, segmenting customers into natural groups you didn't predefine, or anomaly detection finding unusual behavior, like network intrusions or weird credit card transactions that don't fit known patterns.
Finding the unknown unknowns.
You could say that, yeah. And reinforcement learning, as we discussed, truly shines in tasks that need sequential decision-making in complex, often uncertain environments. Think strategic games like Go, controlling sophisticated robotic systems, or navigating those autonomous vehicles through unpredictable traffic.
Sequential decisions in complex worlds. Okay, this really raises an important point then. It sounds like choosing the right type of machine learning is absolutely critical, isn't it? You can't just grab one off the shelf. It has to match your problem, your data, your objective.
Yeah, precisely. That's a key takeaway. It's crucial to understand that each of these types, supervised, unsupervised reinforcement, has its specific strengths, its specific place, and immense importance within the broader field of AI. The choice of which one, or even sometimes how to combine them, fundamentally depends on the nature of the problem you're trying to solve. What kind of data you actually have access to. Is it labeled? Is it not? Is interaction possible? And ultimately, the specific outcomes you're hoping to achieve. There really is no single best type. It's about the right tool for the job.
And that, I think, brings us towards the end of our deep dive today into this fascinating world of machine learning's core types. We really journeyed from the supervised teacher guiding the way with labeled examples to
Hmm.
the unsupervised explorer finding hidden structures in unlabeled data all on its own. And finally, to the reinforcement learner, the agent that gets better and smarter with every action, every reward, and every penalty through interaction. It's so clear that modern AI is really built on these foundational approaches, each offering its own incredible power and specific purpose.
In the continuous development, the subtle nuances, the research happening within each of these fields means we're constantly sort of on the cusp of new breakthroughs, new capabilities. Understanding these foundational differences, the ones we've talked about today, is really key, I think, to appreciating not just the current state of AI, but also its future potential and how these intelligent systems are continuing to shape our world.
Definitely. So maybe as you, our listener, go about your day to day, perhaps you'll start to notice where these different types of learning might be subtly working behind the scenes. From your streaming recommendations, are they supervised, unsupervised, to the navigation app in your car, maybe some reinforcement learning there.
Good examples.
Think about even a simple decision you make today. And then think about how a machine might be trained to make a similar decision using one of these three approaches we discussed. Which one do you think would be most effective for that specific decision and why? It's a fascinating thought experiment.